Alright, so today we're going to do an overview of Unit 4, Topic 2, which is graphs and networks. Now, when we say graphs, I don't mean like a scatter plot or a line graph or anything like that. We're talking about what you would normally probably call a network, okay? And I've drawn a lovely network for you here. So it's a bit of a double naming system that we've called both these sort of networks graphs, as well as, what we do in data analysis. We also call those graphs as well. So just, a bit of extra confusion for you all. Why not? Okay. So first of all, we've got a little bit of terminology to learn. Okay, so these kind of dots here are called vertices, or vertex for just one. Vertex or vertices. The lines are called edges. And then you have some other special names and terminologies. You've got things like this, for example, is called a loop. You can have bridges. There's all kinds of terminology, but the really important ones that you need to know are vertices and edges, because I'm going to be using those words a lot as I explain some of the other things. Okay, so I'm going to first start with planar graphs. Okay, so planar graphs are graphs that can be drawn in a plane. Now, when I say plane, I mean like a two-dimensional space, like a Cartesian plane is a plane. Okay, piece of paper is a plane. Okay, planar graphs are also drawn so that no edges cross. Okay, so for example, if I were to draw a line here, that wouldn't work because now those two lines cross over. Okay, so that would not be a planar graph. Okay, you can rearrange some graphs, so if it does cross over, you can sort of move one around so it doesn't cross over. But if it can't be drawn without crossing over, then it's not a planar graph. Okay, so here's an example. So we'll say not planar if it can't be drawn that way. So a common example is this particular graph that we call K5. It's not that important that you know the name of it, but it has 5 vertices, and it is a complete graph. That's why it's K5, K for complete. So there's one example of a graph that you cannot draw without crossing some lines over. Okay, you're welcome to try, but it can't be done. Okay, so this one would not be a planar graph. Okay, but this other one that I've drawn over here is, because nothing's crossing over currently. Okay, so all planar graphs have a very special relationship between their vertices, edges, and faces. Okay. And we call that Euler's formula, and it looks like this. The vertices, number of vertices plus the number of faces minus the edges will always equal 2. Okay, so you're probably wondering what a face is. Okay, well, a face is any region bound by the edges of a graph. I'll show you what I mean in a second. And there's a special case. We have to include So we have to include the outer region, which is infinitely large, okay? So you're probably wondering what I mean by that. And the easiest way to show you that is with, this is going to sound really naff, but paint, okay? So if I just screen clip my beautiful graph here and I pop that into paint like so, okay, and then I just kind of get rid of that bit there. A face would be, if I take my painting tool here, a face would be any region that will be filled up with paint, okay? So if I put it in here, boop, I filled up that region. So that's one face. Okay, let's try another one. Let's not use blue. There's another face, okay? There's another region that will fill up with paint. So that's 3 faces, 4 faces, but you see there's just one more, okay, which would be everything outside of it as well. Because if you think about it, this whole sort of outer edge is also creating sort of a region, if you know what I mean. Okay, so that goes on for infinity, that outer edge. Okay, because you can almost imagine it wrapping around the world in theory, but we would obviously never draw it like that in practice. So when we think about faces, we've also got to include that outer infinitely large region as well. Okay, so if we use Euler's equation on this network that I've drawn for you here, we have 1, 2, 3, 4 vertices plus 1, 2, 3, 4, 5 faces, okay, which gives us 9. Take away the number of edges, 1, 2, 3, 4, 5, 6, 7. It does in fact equal 2. So that works for this network that I've just drawn. Okay. So that's Euler's formula, and it's written, where is the spelling? It's written like this, so it looks like it's pronounced Euler, or Euler's formula, but he is Swiss, well, he was Swiss, he's dead now, but he was Swiss, so his name is actually pronounced Euler, not Euler. So I just can't help but pronounce it correctly, even though it sounds a bit silly, no doubt. Okay, so what you can see in this equation is that if I were to add extra edges, we can see what might happen, okay? So if I try and add an extra edge here, I've added an extra face. So that would make this become 6, but this become 8. So you can see by adding an edge, I'm making another face, or by adding another face, I have to make another edge. So it just kind of stays in balance when you do that, okay? Maybe I might try and make 2 edges to make one face, but when I try and make another face with 2 edges, I've also had to put in another vertex. So now this is going to be 5, my faces is going to be 6, and my edges is now going to be 9. Okay, so every time I try and sort of beat this formula, it puts itself back in balance. Okay, so that's kind of an interesting situation. Okay, the only way you can break this is if you make it either an isolated vertex or a disconnected graph in some way. Okay, so if I just tried to put an isolated vertex out here, like so, well, yes, now I've broken it, but it's not a planar graph anymore in that case. If I do something like this and call that a planar graph, that's not going to work either because it's not connected. But you could also kind of think of this as being two separate planar graphs. Okay, so for this one I would have two vertices, one face, take away one edge, and you can see I still get two. Okay, so yeah, the only way to really break that is if it can't be drawn without crossing over, like this one here, or if it's disconnected in some way, but you could also imagine that as being two separate graphs. Okay, now that graph can also be drawn as a matrix. Okay, so if you don't know, a matrix is an arrangement of numbers in almost like a table, and it's pretty helpful, particularly if you are programming a computer. Okay, and it can be used in that way to maybe do multiplication or addition. A lot of you saw that there was a question like this on the mock that confused a lot of people. So it was sort of hotly spoken of. So let me show you this drawn as a matrix, and we can talk about matrix multiplication another day. Okay, so what I'm going to do just to help myself out is I'm going to give these vertices names like that, and then what I can do is sort of put it into a table like this, and I can see, well, there's nothing between A and A, there's one path between A and B, there's one path between C and D, sorry, A and C, and there are no paths, no direct connections between A and D. For B, there's one between B and A, none between B and B, one between B and C, one between B and D. For C, I told a lie. There are, in fact, two pathways between B and C. So you can see there's this one here, but there's also this kind of long way around here. So there's actually two pathways. We call that multiple edges. Okay. Between C and A, there's one. Between C and B, there's two. Between C and C, none. Between C and D, one. There is no direct path between D and A. There is one between D and B, one between D and C, and there is one path from D to D, which is that loop there. Okay, so that's how you would turn a graph into, we call this an adjacency matrix. Okay, let me just write that out. Okay, so that's your adjacency matrix. All right, so our next sort of topic that we're going to continue with is now traveling through a graph. Okay, so there's some terminology we need to learn. The words are things like walk, trail, path, cycle, and open and closed. So you could have an open trail or a closed path, or etc., etc. So let's talk about what those words mean. So open, if you see anything where it says it's open, it starts and ends at different places. Okay, whereas closed is where it starts and ends at the same place. I'm also obviously particularly talking about a vertex there. So it starts and ends at the same vertex. I'll give you some examples of these in a minute. Okay, so if you ever see open, it means it starts and ends at different vertices. If it's closed, then it starts and ends at the same one. Okay, so now you've got that. Let's talk about walks, trails, and paths. So I like to kind of draw this diagram like this, because they're kind of concentric circles in the sense that they one is a kind of a subcategory of another. Okay, so a walk is kind of the umbrella term, and a trail is a kind of walk, and a path is a kind of trail, if that sort of makes sense. Okay, so a walk is any route through a graph from one vertex to another along the edges. So basically it's just any route through the graph. It's really open umbrella term. Okay, I'll give you some examples now. So let me just draw up this quick little network here. Okay, it's going to have a few different features on it. And I'm going to get my highlighter out. We're going to have a look at some different ways to travel through it. Okay. Just draw that a little bit nicer. Okay, so each of these dots is a vertex, and we've got our edges. Let's have a look at how we can travel through this network. Okay, so let me just grab my highlighter real quick. Okay, so a walk, an open walk might look like this. A little bit this way, this way, this way, this way, this way. Okay, so that was an open walk. Okay, I'm just moving from vertex to vertex along the edges. I've got some repeats in there, but it's open because I started and finished at different locations. Okay, so let's do a closed walk. So maybe here, 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 and we're back to the same place. Okay, so that was a closed walk where it started and finished at the same place. And as you can see, we've had a little bit of overlap, okay, in both vertices and edges. Okay, so now that we have seen what a walk is, let's talk about a trail. So remember, all trails are walks, okay, but trails are special in that they have no repeated edges. Okay, but they may have repeated vertices. Okay, so let's maybe come up with an example of one of those. Okay, remember they can be opened and closed. Okay, so an open trail might look like this. Okay, it's open because I started and finished at different places, and it's a trail because I haven't repeated any edges, but you can see in the middle of the in the middle of the graph, I did go back to that vertex twice. Okay, so that makes it an open trail. Okay, let's try a closed trail now. Okay, so a closed trail might look something like this. Okay, there's a closed trail. So I haven't repeated any edges, but I have repeated a vertex up here. Okay, because when I went around the loop, that was going back to that vertex a second time. Okay, so that's a trail. Let's try a path now. So a path is a trail that does not have any repeated vertices. Okay. The only repeated vertex it can have is if you have a closed path, and obviously you are going to start and finish in the same place. Okay, so we will except for the start / finish. Okay, now like I said, only for a closed path, not for an open path. Now, a closed path has a special name. Okay, so a closed path is a cycle. Okay, so that's the only one that has sort of its own special name. Okay, and it's fairly self-evident as to why it's called a cycle. Okay, so here's an example of an open path. Okay, I haven't repeated any vertices, I haven't repeated any edges, and it's not finishing in the same place as it started, so it's open. And then obviously if I wanted to make it closed, I could very easily just add that line in there, and now it's a cycle. Okay, so that's your different terminology there. This is going to be important because we're about to build on it with the Eulerian and Hamiltonian graphs in just a second. Okay, I will have some practice questions after a while to see whether you're understanding this. Okay, so let's move on to our next topic, Eulerian graphs. Okay, so I'm just going to draw you some graphs, and you can sort of see if you can spot some of the similarities and differences between them. Okay, so here's my first one. Okay, there's my first graph. Here's my second graph. And here's my third graph. Okay, so you might notice that they do have some similarities to them. Okay, and they're going to have different properties because of sort of some of their features there. But what I want to ask is, can I walk on every edge of these graphs without having to lift my pen? Okay, so using my highlighter, can I go over every single edge without having to lift my pen, okay? Now, let me see if I can do that. So I'm going to start over here, so remembering where my starting position is. I'm not even really going to try, I'm just going to see what I can do. Doesn't matter if I revisit a vertex, I'm mostly just interested in edges. Oh, that was really easy. Did that one, and I started and finished in the same place. Okay, interesting. Let's try this next one. This time I'm going to start here instead. Okay, let's see whether this is going to work. Da 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 da. Okay, so I started in one place and I finished in a different place. Okay, but I was still able to go over every edge. Okay, now I'm going to try this other one. Let's start over here. Da 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 da. Oh, okay, that didn't work. Let's try a different way. Da 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 da. No, okay, still no good. Maybe if I start in a different place. Da 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 da. Okay, still not going to work. Okay, and you're welcome to keep trying this, but this one is never going to work. Okay, these two are. This one's not. Okay. Now you'll also notice if I just add this extra line over here, okay, to make it look like my second graph, if I start in a different place, let's say I start here, it's also not going to work. Da, 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 da. Oop, see, already broke it. Okay, let's try a different one. Da, 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 da. So close, but still didn't make it. Okay, so what we can conclude is one of these works all of the time, one of these works some of the time, okay, and one of these never works. Okay, so let's have a look at what's different between them. Okay, and what you need to know about is a term called the degree of a vertex. Okay, it is the number of edges attached to a vertex. Okay, so let's start counting the degree of each of these vertices, I should say. So this one has a degree of 2. 1, 2, 3, 4. This one has a degree of 4. 1, 2, 3, 4. 2, 4, 4, 4. Okay, let's try this next one. See if you can notice a pattern. So this one only worked if I started and finished in certain places. Let's count the degrees of the vertices. So that one's 2. This one's 3, 4, 2, 4, 4, 3. Interesting. And this last one is 2, 3, 4, 3, 3, 2, 3. We're noticing a bit of a pattern. Okay, so why does the first one work every time, no matter where I start, and I end up in the same place as I started? Why does the second one only work if I start in a particular spot? And why does the third one not work at all? Okay, well, it's because of their degrees, the degree of their vertices. Okay, so you'll notice that this first one, all of the degrees of each vertex are even. Okay, the second one, all of them are even except for 2. And you notice the 2 odd ones are my start and finish places. Okay, interesting. And then the third one, there are more than 2 odd degrees there. Okay, which is why it doesn't work at all. Okay, so we call this first one Eulerian. The second one is semi-Eulerian. And the last one is not Eulerian at all. Okay. So basically an Eulerian graph is one where you can travel on each edge once. You will start and finish in the same place. And you know it's Eulerian because every vertex, the degree of every vertex is even. Okay, so you can pretty much tell straight away without even having to do the travel through the graph that it's going to be Eulerian and it's going to work no matter where you start. Okay. Whereas the semi-Eulerian, this is still fine. So yes, you can travel each edge once. I forgot the word travel there. You can travel on each edge once without repeating, that is. However, you will start and finish in different places. And the degree of every vertex is even except 2. And you have to start and finish, actually end at the odd ones. And then the non-Eulerian is you can't do it. You can't travel each edge. Without repeating, so you just can't do it, okay? So Eulerian is every degree of each vertex will be even, and you can start any vertex you like. You will walk over every edge and you'll end up in the same spot every time. Semi-Eulerian, you can do it, but you have to start and finish at the 2 odd vertices. And then if you have more than 2 odd vertices, it won't work at all. Okay? So you have to remember about Eulerian graphs. It's mostly about can you walk on every edge. Okay? So it's about the edges, and Eulerian graphs are also mostly aimed at trails. Open and closed, obviously. So because they contain trails, it means it's okay to repeat some vertices. Okay. That's in contrast with our next topic, which is Hamiltonian graphs. So instead of wondering if we can walk on every edge, the question becomes, can you visit every vertex? Okay, so Eulerian is about walking on the edges. Hamiltonian graphs is about visiting the vertices. Okay. Here's, let me just draw that another graph for you. Going to look quite similar again. All right, let's see, just with our highlighting tool again, is it possible for us to visit every vertex? Okay, so let's give that a shot. Let's see if we can start and finish in the same place again. Okay, so let's just try going around the border. Good place to start, and we can go in. Lovely. Oh, that was easy. Okay, so we can call that a Hamiltonian cycle. Why is it a cycle? Well, because we started and finished in the same place. Okay. There's no real trick to these Hamiltonian ones. You just kind of use trial and error and hope for the best. Okay. Now, the other thing I could do is not start and finish in the same place, start and finish at different places, and that would look like this, perhaps. Okay. So you can see now I have visited every vertex, but I also didn't start and finish at the same place. So we call that a Hamiltonian path. Okay, because it's open. And we know that a cycle is closed. Okay, so Hamiltonian graphs are much easier because there's no trick to them. You're just using trial and error. You're just kind of using your reasoning skills to work your way through it. Okay. So remember we mentioned the example before was about, can you walk on every edge? That was our focus. Can you walk on every edges? And it didn't matter if we repeated some vertices. Okay, well, in Hamiltonian graphs, we're interested in, can you visit every vertex, which means that it's okay if we don't walk on every edge, if we don't travel to every single edge. And as you can see, I've left this one out, and I've left this one out. Okay, so there are some that I've skipped, and that's fine. Okay, so Hamiltonian graphs contain paths. And cycles, which is a closed path, which means that it's okay if you don't travel on every edge. Okay. There's one more little subtopic in this unit, which is weighted graphs and the shortest path. Okay, so you're probably wondering what a weighted graph is. Well, a weighted graph is one of those graphs as we were looking at before, except it has values on it of some kind. Okay, so if I draw this graph out again, okay, and let's say this is maybe roads to different towns, and they might have distances in kilometers on them. Obviously not drawn to scale. I'm just putting random numbers on here. Okay, so if we wanted to get from A to B, what would be the shortest way to do that? Okay, so you're welcome to do this as trial and error. But I like to add a little bonus extra to it. And what I do is I sort of do a accumulation of distances as I go along. Okay, so for example, I know this one's 12. Don't get confused with critical path analysis, though, is the trick. That one's 5. So what's the shortest way? Oops, I didn't put a number on some of these. Let's call this 14, and you can be 7. Okay. So what's the shortest way to get to this node here? Would it be 5 plus 7, or would it be 12 plus 22? Well, it's obviously going to be 5 plus 7. So that's 12. So just see how I'm adding as I go along. It just makes it easier to keep track of where I was going. Okay, so to get to the node down here, it would be probably shortest to do 12 plus 4, not 19 plus 5. So that takes me to 16. Okay. Up here, I can either do 12 plus 14 or 12 plus 6. Obviously, 12 plus 6 is going to be the way to go. Okay, and I just try and put arrows so I remember which way I took to get there. Okay, and then to the last node, which is my final destination, do I want to do 16 plus 20 or do I want to do 18 plus 34? Well, obviously, I want to do this one, which gives me a shortest path of 36. Okay, so that's how I do shortest path, and you can sort of finish up by highlighting that final path that you took, which was that way. Okay, but you can just kind of use trial and error and just see what the quickest way is. Not too tricky on that one. Okay, let's do some practice questions now. Okay, so what I've done is I've dug up some of the questions from the QCAA samples. So what I'm going to do is I'll put it up here. What you should do is pause the video, have a go at it, and then I shall reveal the answer. Okay, so pause the video, have a go at this question. Okay, assuming you've already answered this one, the answer to this question is 4. Okay, so if I mark on here what is the degree of each of these vertices, so this one's got 3, this one's got 2, 1, 2, 3, 4, 5, this one's got 5, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. You can see this is the smallest one and is being called vertex 4. I think this one here is supposed to be a trap. Okay, so keep an eye out for something like that, because it's not asking what is the smallest degree, it's asking which vertex has the smallest degree. Okay, so keep an eye out for that sort of shenanigans. Okay, here's your next question. Pause the video, have a go. Okay, so let's draw this little travel through this graph. J, R, M, P, P, Q, like that. Okay. Now this one's a bit different because it has the letters on the edges instead of the vertices, but you should still be able to adapt pretty well for that one. Now, it can't be a path because there are repeated vertices. I've been to this vertex twice, 3 times. Can't be a cycle because it's open and also it has repeated vertices. Can't be a trail because I went on edge P twice, so it must be an open walk. Okay, I did not start and finish in the same place, so that makes it an open walk. Next one. Pause the video, have a go. Okay, the answer to this one is B. So we've got 1 face here, 2 faces, 3 faces, and then the infinite face that is everything else. So that is 4 faces. Okay, so the answer to that one is B. Okay, pause the video, have another go at this question. All right, the first thing you should do for this question, because it already tells you that it's semi-Eulerian, so that means you should be listing the degree of each vertex. Okay, so let's do that. 2, 3, 2, 4, 2, 6, 3, 4, 4, 2. And you can see they are all even except for 2. So D and J are your start and finish places. Okay, so you need to either start at D and finish at J, or start at J and finish at D. Okay, and while you're doing that, you need to count every town that you pass through. Let's start at the first one. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, so we went to 17 towns while we were driving on every road. Okay, now I believe in external exams you're not allowed to just highlight your answer, so you would actually have to write out what path you went on. But essentially 17 towns, $5 per town is $85. Okay, but make sure you show all your working. I'm just trying to do this nice and quickly. Here's your next question. Pause the video, have a go. Okay, so let's highlight a Hamiltonian cycle. So start and finish at the same place, and we just want to go to every vertex. Okay, so something easy might be this way. Okay, nice and simple. But you'll see that there's 3 edges there that we did not travel on, and remember that is okay in a Hamiltonian path or cycle. So the only roads we haven't been on are A, C, B, D, and C, D. Okay, and remember, do in your Hamiltonian cycle write out the whole path because like anything just highlighted won't be accepted. Okay. Now for the Eulerian graph. Let me just get this out of the way. Once again, you need your degree of each vertex, like so. And you can see there's 2 odd ones, so we need to either start at A and finish at B, or start at B and finish at A, whichever you prefer. So let's... Ta-da! Okay, So that would be your Eulerian trail that you're walking on there. Okay, it asks you to justify decisions made, so you would have to use, your justification would have to be things like, it's a semi-Eulerian graph because all of the degrees, all of the vertices have an even degree except for 2, so I have to start and finish at those places. Okay, so that's sort of what it means by justification. Okay, here's another one. Pause the video, have a go. Okay, so once again, let's list our degree, the degree of each vertex. So 1, 2, 3, 4, 4, 2, 4, 2, 1, 2, 3, 4, 5, 6, 2. So we have all of them are even, so that means you can start and finish at any place you want, and you will walk on every edge without having to repeat an edge. Okay, so I believe it says she has to start and end at the depot. Is it possible? Yes, it is. So if I just go do, it will just happen really nicely. Okay, but then I could have also started at the pharmacy and that would have worked just as well. Okay, have a go at the next one. Pause the video. Okay, so this is a shortest path situation. So let's start working our way through the network. So to this node, I would put 47 and I went this way. To this node down here, the quickest way is actually 60 going that way. So 47 plus 13 is shorter than going 62. Okay, the shortest way to this node up here, is this way. 47 plus 48 is 103. The shortest way to this node is 103 this way. So it's actually quicker to go across 3 different edges than it is to take just this one edge down the bottom. Okay, which means that the fastest way to get through it is this way. Okay, so that's my shortest path. I'll just highlight it for you so you can see. That's it there. But remember, make sure that you write out your answers. Highlighting does not count. Okay. Next one, pause the video, have a read, have a go at the question. Okay, so this one is going to be a Hamiltonian cycle because we want to start and finish at point A and we want to visit every vertex once without doubling up. Okay, so as I mentioned, you're just kind of using trial and error. This is the way I've done it. There are definitely other options, but here's what I've done. There we go. Starting and finishing at A, and we have been to every checkpoint once without doubling up. Yes, there are some edges we haven't been on, but that is okay. We don't need to since it's Hamiltonian. Okay. Last one. Pause the video, have a go. Okay, so we need to travel on every street in this town. Okay, is there an efficient sort of route that we can take? Well, yes, there is. Let's put our degrees in. 1, 2, 3, 4. 1, 2, 3. 2, 1, 2, 3, 4, 5. So you can see they're all even except for F and G, so we need to either start at F and finish at G, or start at G and finish at F. Both will work. And you'll notice you don't even really have to put much effort into these ones. They just kind of work out, which is kind of beautiful. Ta-da! All done. Okay, it's just the Hamiltonian ones that take a little bit more effort because there's no trick to them, just trial and error. Okay, well, feel free to put anything in the comments if you are still stuck, and I'll see what I can do about answering them. Good luck.